Hello, I'm Zay Fackenthal,
And I'm David Johnston.
and this is our Project 4 for differential equations, finding the perfect temperature of a cup of coffee that neither of us are going to drink.
No.
Because we don't like coffee, as we will make known to you throughout this presentation. All right, continuing on.
All right, so your cup of coffee is made in a cafe by pouring 200 degrees Fahrenheit water through freshly ground coffee beans. After 2 minutes, the coffee is 190 degrees Fahrenheit. The surrounding air temperature is 70 degrees Fahrenheit. 3 temperatures mark the drinking experience. Liquids above 160 degrees will scald the mouth and burn the tongue, which is not fun. At 140 degrees, the aromatic flavors of coffee shine, apparently. Again, I don't actually know that. Until it becomes too tepid below 120 degrees, which is also apparently a bad thing. And then you can see at the bottom we have our Newton's law of cooling, which is the differential equation we'll be solving throughout this presentation. Words. Okay. Some of our assumptions. We're assuming that change in temperature is relatively constant in a given set environment. By this we mean like room temperature is constant, no other outside forces, forcing functions like blowing on the coffee will be in effect, so it'll kind of it's cooling down at the rate it should be if it was undisturbed and unmessed with. We're also assuming that there's uniform constant pressure in the room, again, for the same reason of nothing's messing with our cooling process.
All right, the first method we're going to show you to solve this differential equation is a separable method. We won't go into too much depth about these following ones, except the fourth one, the Laplace, because that's the one we're really focusing on in this presentation. But back to separable, the goal of this is to separate the function in terms for x in terms of t, so that if you're able to do that, you can then integrate and get a function of just x, as you can see right there, which is equal to a, our room temperature, minus some constant c and some constant k. We can solve for c and plugging in our initial condition at time is equal to 0, canceling out that whole part with e. And then once we get c, we can plug that into into the middle equation right there, solving for k, where we plug in t is equal to 2. And then we get our value of k, which is roughly 0.04. And we get our final solution to this differential equation, which we'll be solving for a couple more times. If we move on to the next method, we have our integrating factor method, which in this case involves kind of a reversal of the product rule, where if you see actually on the left where we have e to the kt times x, and then the first derivative of that, if you were able to split that up, you would get e to the kt x prime plus k e to the kt x. And if you look back at the first step, that would be the same thing as if you multiply e to the kt across the entire function. So if you do that, you're able to get a form where you have x is equal to a minus some constant e to the negative kt. Again, c is a constant, so it could be plus c. Either way, we'll solve the same way we solved the previous equation, and we get our same equation.
Cool. And now we're looking at our characteristic equation and undetermined coefficients method. Again, it's a lot of the same stuff, but in this case we're going to take the characteristic equation of our x prime plus xk equals ka, which we then solve for r, and from there it's the same thing. It's the exact same thing, more or less.
What differentiates this from our previous ones is that now you see we have x prime isolated on one side and everything else on the right side. Yeah. X prime, the functions of x, so we move x over, and then we can use the characteristic equation method.
Yeah, more or less. All right, now we're looking at the Laplace transformation method. In this, we're going to start with the same x prime plus kx plus k, or equals ka. We're then going to take the Laplace of both sides, which is going to give us our s plus kx equals k over s plus x naught. We're then going to solve for x, and then via partial fraction decomposition, we're going to get to the equation on your right. I didn't have to check that. We're going to get to the equation on your right, And then solving for the parts, you'll see that we have the equation Ka equals A times S plus K plus BS, which allows us to solve for A and B, which are partial fraction decomposition, A and B. And we're just going to use big A because big A is already being used, so but then, A equals our big room temperature, and then B equals negative room temperature. And then from there, it's effectively plug and chug again. We plug it into the equation that we have, which is the 190, we plug in the x of 2 equals 190. That gives us our 190 equals 70 plus 130e negative 2k, which solves the same way, and we get the same equation.
A couple more pointers on this slide is that we're able to take the Laplace because our initial function is exponentially bounded. And then the reason why we have our Ka divided by S, might be curious to you where that S came from, is that when we're ever doing this, we're looking at our basic table of transforms, and Ka is just a constant. So that would turn into 1 over S.
Yep, here we go. Oh, this is still me. Okay, cool. So, with then taking that equation that we've now solved for 4 times, we can then solve for the time it takes to reach certain temperatures. So the time it takes for it to reach the threshold of scalding is 9.2 minutes. And then the time for it to reach that peak temperature of 140 is 15.5 minutes from when it was first brewed. And then until it's too cold is 23.9 minutes. That gives us a time to enjoy the coffee of only 8.4 minutes. So basically the moment it hits 15.5 minutes, you got to start drinking pretty quick.
Right. Keep in mind that this is all still in the cafe shop. This is all in one room.
Yes, we're not changing rooms yet. Yes. Speaking of which.
All right, now we are changing the environment, and now there's going to be a discontinuous temperature change depending on the environment we are in. So instead of waiting in the coffee shop until it's ready to drink, like in the previous step, now after 2 minutes, you're going to walk outside where the temperature is 40 degrees Fahrenheit instead of 70. And then 8 minutes after that, or 10 minutes after you first got your coffee, then you're going to go back into, let's just say, your dorm room where it is back to 70 degrees. And our goal with this is to see now, like in the previous slide, when is the perfect time to drink the coffee, now that we actually have a discontinuous set of data. So when we're solving for Laplace, it's the same. You see we have our x prime plus kx is equal to ka. That's nothing different. But now we have this unit step function. Now we have negative ka plus kb, or subtracting the initial temperature and then adding the new temperature. So that's necessarily just minus 30. And then when it gets back to 10 minutes later, now bringing it back up to 70 and getting rid of the previous 40. So if we track that down, when we take the Laplace of one of these things, we get this activation component, this e to the negative 2t. This is how we remember that, hey, this is being shifted over to be activated at this time later. And then again, these are this changes, they're still constants. So using the basic table, that is still 1 over s. And then if you see on the right side there, we are adding our initial condition of x of 0, and this is because this is just a first derivative differential equation. We're only adding that one constant, and there's no multiple of s to that. So now if we solve for x, dividing that s plus k down to the bottom, we get what we're going to try to take the inverse Laplace now, but it's nothing pretty. So we're going to use partial fraction decomposition for that Ka, the first thing, as we did previously. And then on the right side, both similarly have the Ka minus b over s plus k. So we can solve using partial fraction decomposition to get the appropriate little a and little b for both of those. A being a minus b, and b being the negative of that, similar to the previous slide where it was a and negative a. So now that we have this broken up for partial fraction decomposition, now we can take the inverse Laplace back, bringing it back to the x of t, where now we have the a constant, and now we have this. I'm not even going to explain it. There's that huge equation right there. But the important thing is we get back that unit step function. Now we get that. Now that's being shifted over. At what time does this new component of our function take into effect? And then we can plug in k, and we can plug in a and b. A being again room temperature of 70. B being 40, so that's where we get 70 minus 40 is 30, and we get our equation. Yes. All right. Oh. Can't get you too excited. Now, reflecting on our data, we threw that equation into Desmos as if it was like a piecewise function. And you can see the first purple step is up to 2 minutes, and the black is from 2 to 10. Yes, and then the rest of the purple is 10 on. And you can see the moments, red, orange, and blue, for when we hit that 160, 140, and 100 degrees Fahrenheit.
120, but yes.
120, correct. And we can compare this to our previous data to see what is it like now that we have moved outside. You could see that the time is actually decreased, and this makes sense because you are going into a colder environment. The coffee is going to get colder sooner, so you're going to want to drink it sooner. And if we actually look at when the appropriate time to drink it is at 140, at t is equal to 13 on the dot, you see that is a part of the purple, the second purple function, or when you have gotten back in your dorm room. The difference is roughly 2 minutes between each of our times, as I said previously. And does it make sense for you to stay in the cafe? I'd say no, because you are able to get to your room and be able to drink your coffee sooner rather than if you were in the coffee shop. If it got to that prime temperature in that moment you were outside, then I'd probably say no, because it's nice to drink coffee from what we have experience with in a nice warm environment. And then to point out our Desmos equation right here, it's important to show that it is non-smooth because it is not one it is not one function. There are points of where it's non-differentiable, where if you think of it as a piecewise function, you can't find the slope in between two different points, right where they intersect. It may be continuous where they line up, but it's not. There's those points of discontinuity. Yeah,
that's it, I think.
Yeah.
Well, actually, that's
there
it.
We go.
There we go.
The end. And neither of us drink coffee.
Yep. All right.
I hope you've enjoyed this presentation, because we have.
Except the coffee.
Except the coffee.
Yeah.